Welcome back to EasySpin Academy 2020, Day 3. This is the session on ENDOR spectroscopy. Before that, we saw that a bunch of folks joined after the beginning of the first session. So let me summarize some of the announcements again. For questions during the sessions, please head over to Slido. The link is on the Academy website, easyspin.org/academy. You can also download the complete session scripts, including the ones for the last 3 sessions of today that where the topics weren't finalized until this morning. The old videos of the previous days and also of this day will be available on YouTube, and so you can rewatch this anytime later. And there will be an exit survey that will be sent out via email. It also will be available on the Academy website. And don't forget, if you want a t-shirt, buy it now or within 4 days because the campaign is going to close. And I hope to see you all on a happy hour at the end, after the end of the last session. With this, let's go in and look at what EasySpin does for ENDOR. So there's 2 functions that support ENDOR simulations. One is dedicated to ENDOR and it's called SALT. The second function is Saffron. And that function simulates specifically MIMS ENDOR spectra. So let's start out with SALT first. Start out with a clean slate. Set up a system with a G value of 2, nucleus of a proton, a 10 megahertz hyperfine coupling, and some very narrow broadening. Let's plot the EPR spectrum first. So let's define the experiment, the EPR experiment first. So with a microwave frequency, let's say 9.5225 gigahertz as usual. Let's make a subplot, a 2x1 arrangement of plots on the figure. And let's plot the solid state spectrum in that first figure. So we're going to call Pepper with a spin system and the EPR experimental parameters, which in this case is just the microwave frequency. If you run this, we do get the first plot. And as expected, you have 1 proton, so we expect the EPR line to split into 2. And the spacing is 0.35 millitesla, which corresponds to 10 megahertz. Now next, let's add the ENDOR spectrum. So we define an ENDOR spectrum, exp ENDOR, just to make it, to distinguish it from the EPR parameters. We'll set the field now to, what value you set it to, like 340.2 millitesla. And we set, so we kind of set it here to the center of the EPR spectrum. And we're gonna set a range for the nuclear frequency, for the radio frequency. Let's go from 0 to 30 megahertz. And finally, we have to tell EasySpin about some broadenings of the ENDOR lines. And those broadenings can have a variety of origins. One of them is some structural variation between different molecules, very similar to G and A strain, or A strain in particular, that we used for EPR spectra. In addition, ENDOR spectra can be broadened, power broadened. So if the RF pulses are short, their excitation bit is fairly large, and that might broaden some of the sharper ENDOR features. Both effects can be just roughly be modeled phenomenologically using a convolutional ENDOR line broadening, and that is called LW ENDOR. And we can set it to 0.2 megahertz. So now let's set open subplot 212 and call SALT now. SALT will return or plot an ENDOR spectrum. It takes the same type of inputs as any other simulation function, the spin system, and the experiment parameters, which is exp ENDOR in our case. Okay, now if you run this, we get the ENDOR spectrum. We see 2 absorption lines split by 10 megahertz and centered around the nuclear Larmor frequency. We can actually add a line for the nuclear Larmor frequency. First, we need to calculate the frequency using the function Larmor FRQ, which I've showed you in a previous session. So we have a proton, and we are at the field that we've just defined above, exp ENDOR.field, we can just reuse that variable name here instead of typing in the numerical value again. So if you change the field up here, it will automatically propagate to this, and you don't have to type in the number twice. And now in order to add a vertical line at a specific x value, we just say x line, that's a MATLAB command, at this particular frequency. So we're going to run this now, and there you go. We do have a vertical line that shows where the nuclear alarm frequency is. Now we can rerun all of this with more protons. Let's add 2 more extra protons, and let's add a few isotropic hyperfines, let's say 10, 3, and 2. And if you rerun this, we'll see that the EPR spectrum now consists of 8 lines, which is 2 times 2 times 2. And the ENDOR spectrum only consists of 6 lines, which is 2 plus 2 plus 2. Right, 2 for each proton. This is just very simple simulation using SALT and an isotropic hyperfine couplings. Of course, we're not limited to that. SALT can also treat general spin Hamiltonians. So let's look at the ENDOR spectrum of an anisotropic system. Again, clear out everything, maybe even the figure. Define a spin system with a G value of 2, a proton, and now we take a hyperfine coupling that's axial with 5, 5, 10 megahertz. And then some ENDOR broadening, which again could be some distribution of A values or power broadening due to the RF pulse. And then let's add a static field, maybe 350 millitesla. Let's specify a frequency range between 5 to 25 megahertz and run SALT, providing the spin system and the experiment. As you can see, it's very, this workflow for simulating EPR spectra is always the same, no matter which experiment you're simulating. You define your spin system, you define experiment parameters, and you call the simulation function. Here we go. There is now the ENDOR spectrum still consists of 2 features centered around the Larmor frequency, which is still about 15 megahertz. We have a low field peak and a high field peak, and they have roughly the same intensity, not quite. From like basic, EPR 101 considerations, you would expect the same intensity. However, the splitting is relatively large compared to the Larmor frequency, right? The splitting is up to 10 megahertz, and the Larmor frequency is about 15 megahertz. And this puts us into a out of the perturbation regime, and we get some second order perturbation effects, which will render this line shape a little narrower than this line shape here. And as a consequence, this line shape is a little more intense than this here, which is lower in intensity. If you go to higher fields, then of course we would go back into the first order perturbation range, and the intensities would become more equal. Actually, we can test that right away. Let's go to W band. It takes only 3 lines of code. If you would go into W band in the lab, it would cost you probably a 7-digit number of money, and maybe a year or 2 before you get it. Okay, so experiment fields 3350 millitesla, and the range we're going to sweep from 135 to 150 megahertz, and then we again call SALT with system_exp. So all I've done here now is change the field and the RF sweep range. I'm selecting the code here and then evaluate only this selection by pressing F9. And here you can see now the results. The Larmor frequency is about 142 or 143 megahertz. The 2 peaks are centered around that, and they have basically equal intensity because we're in this first order regime now. So that is actually a strong argument for going to higher fields. ENDOR spectra often simplify considerably. Okay, so far we've actually, let's go back to the EPR spectrum. So far we've simulated these spectra. I'm going to run this again and trim this down just to 1 proton. Again, so here is the spectrum, EPR spectrum on top and the ENDOR spectrum on the bottom. So far, we've simulated this with infinite excitation bandwidth, right? We put the microwave right centered at this field and we just could excite everything. However, if we change the microwave to somewhere else, sometimes we might not hit these transitions because we're off resonance and we shouldn't see any intensities. If you don't specify an excitation bandwidth, EasySpin assumes infinite excitation bandwidth, and that's of course not very realistic. So now let's look at what happens if we limit the excitation bandwidth that the ENDOR experiment has to make it more realistic. Clear up everything. I'm going to copy over a spin system here. So this is a spin system with a slightly anisotropic G tensor, 1.9, 1.98, and 2.12. One proton with an axial anisotropic hyperfine interaction tensor. And the EPR spectrum has a broadening of 5 megahertz. We're going to simulate the frequency domain spectrum. Okay, so in order to simulate the frequency domain spectrum, frequency domain EPR spectrum, we'll have to define a fixed field, which we take again at X-band, 350 millitesla. We define a large number of points to make sure we have enough resolution. And we want to look at the absorption spectrum, x dot harmonic equals 0. So we're going to start subplot 211 just to put the EPR spectrum again in the upper part of the figure and call pepper cis comma exp. If you run this now, we will see here a frequency domain spectrum at fixed field. The field is 350 millitesla, and the horizontal axis shows the frequency going from 9.2 to 10.6. As you can see, it's a rhombic spectrum, and if we zoom in nicely here, we can see there is some traces of the hyperfine splitting visible, right? But of course, these couplings are extremely small, and they're barely visible in an EPR spectrum. They're not resolvable, even as low field edge. Typically, line widths are much broader, and if you have a line width like this, then any hyperfine splitting is gone, even though the hyperfine coupling is still exists in the spectrum. And that's the reason why we do ENDOR in the first place, to resolve these unresolved hyperfine couplings. Okay, let's go back to a narrow, artificially narrow EPR line width. Okay. So next, let's simulate the ENDOR spectrum. We're gonna first define an experiment, ENDOR, exp-ENDOR field. And we're gonna set that field to be exactly the same field as we used for the EPR simulation. Because after all, that's how ENDOR is done, is you put your sample in, and then you fix your field, and you perform your ENDOR experiment. Exp-ENDOR dot range, we're gonna sweep from 5 to 30 megahertz. And now let's ask SALT to return us the simulated spectrum and the frequency axis. So new for the frequency axis and SPC0 for the spectrum is SALT cis comma exp-ENDOR. So this will calculate the ENDOR spectrum that is still has infinite excitation bandwidth. You see, I didn't specify any microwave frequency, because if you have infinite excitation bandwidth, it really doesn't matter what microwave frequency you use. So this is infinite excitation bandwidth, ENDOR. Now let's simulate ENDOR with a finite excitation bandwidth. And to do that, we have to supply two things. We have to tell which microwave frequency we're working at. And now let's actually look which microwave frequency we should use. If we use 10.6, we're going to be off resonant. We're probably not going to get any ENDOR spectrum. So we should be somewhere within the EPR absorption line shape. We could just start out near the maximum of the EPR spectrum, which is roughly 9.7 gigahertz. So 9.7. Then again, we need a RF frequency sweep range. Just go from 5 to 30 again. And actually, we already have that defined. We don't have to spell it out again. But the second thing we need is the excitation bandwidth, excite width. Now SALT simulates ENDOR spectra, and it has an approximation to treat excitation width. It just models it as a Gaussian excitation profile. You can use Saffron and Spidian, which are other EasySpin functions, to model a more accurate excitation profiles. But very often for simple ENDOR simulations, assuming a Gaussian excitation profile is sufficient. And in excite width, what you do, you need to provide the full width half maximum of that Gaussian excitation. And you're going to put it in megahertz. So 50 megahertz means it's basically just a sliver, a really tiny sliver around 9.7 gigahertz that's being excited. Okay, we'll have to increase the number of knots because we'll see we'll have a lot of orientation selection here, which is a consequence of this narrow excitation bandwidth. Now we're going to simulate the spectrum. We should probably add overall a ENDOR line broadening, sys.lw ENDOR. And 0.2 is probably, megahertz is a good starting point. So now we want to simulate this finite bandwidth ENDOR spectrum. So we provide the system and the experiment definitions that now include the microwave frequency and the excitation bandwidth, which are the two important ingredients. So I will run this, but first let me write out the code to plot the results. So infinite excitation bandwidth and finite excitation bandwidth. So we're going to open another plot at the lower section of the figure. We're going to plot nu and spec 0 divided by its maximum, just to normalize it to 1. And we're going to plot nu and spec 1 divided by its maximum. And just to make it clean, we can put an X label onto it. X label, frequency in megahertz. And we can put on a legend that says infinite excitation bandwidth and like 50 megahertz excitation bandwidth. Okay, I think we are ready to run this by just pressing Control Enter. And now we'll simulate TPR spectrum and the two ENDOR spectra. And here's the result. On the bottom, you see we still have the Larmor frequency at the center with two features to the left and the right. In blue, you see the infinite bandwidth ENDOR spectrum, which you can't ever get experimentally. And in red, you see one with a 50 megahertz excitation around the center. And you can see for these orientations here, the hyperfine couplings that are resonant, of the spins that are resonant, are more close to 5 megahertz than to 10 megahertz. What we can do now is we can change the resonance frequency or the microwave frequency to walk across the spectrum. For example, we can set it down to 9.3 at the lower frequency edge of the spectrum. So if you change this 9.7 value to 9.3, we'll see that the peak really sharpens up because now we only excite a very small fractions of the overall spins in the sample. And all those that are resonant at this frequency all have the same orientation. So this is almost a single crystal-like ENDOR spectrum that results. We can go to the high field edge at 10 point, maybe let's go sit at 10.38. 10.38, Control Enter. And what you see now is that if you sit here, we're going to hit orientations where the large hyperfine direction is active. So the 10 megahertz, the Z direction. And the ENDOR spectrum shows again just two sharp lines, single crystal-like, at the that are separated by 10 megahertz. And what we can now do, we can again use this little tool. When you right-click on a number, click on Increment Value and Run Section. I'm going to change the resonance frequency by 0.1 at a time. And if you decrease it, we're going to kind of walk slowly across the spectrum, starting from the high frequency end to the low frequency end, and just observe what happens to ENDOR. The line gets broader. It even shows substructure, which is just a result of the orientational distribution and the selectivity due to the G anisotropy. Now we're at 9.7, which corresponds to the spectral maximum. And as we go further down, we have an axial hyperfine. Now we're at 9.3, and we see we get a very sharp line again. So this is how excitation bandwidth limited ENDOR simulations work. Let's go back to the center, and now let's finally look at this warning we get all the time. The warning says there is strong orientation selection, that only 1.4 of the calculated orientations are within the excitation window. So basically what EasySpin does, it tries out all the orientations of the molecule and sees whether they're excited with this particular narrowband excitations. And it turns out only a very small fraction of them are excited, so the simulated spectrum does not have a good orientational averaging in it. So the warning tells you what to do. Either increase the number of knots, so the number of orientations, so that's fixing it on the simulation side, or increase the excitation bandwidth, which usually, of course, we can't do because it's fixed by the experiment that we've done. So let's increase the number of orientations. Let's bring it up to, like, let's say 400. What we forgot to feed in opt to salt. That's why we still get the same error message. Okay, so I changed n knots to 400 and included opt as a third parameter to salt. And we need this only for the finite excitation bandwidth simulation. Now, of course, this will take a little longer. It's still running. You can tell that from here where it says pause. If it's done running, there's a run button here. And now it's done. And you can see the spectrum is still smooth and there is no warning. Now you can be confident that you got some good orientational averaging. So this is called orientation selection, or bandwidth limitation, or finite bandwidth excitation. And it's a really important aspect in solid state EPR if you do any experiments like ENDOR or ECM or deer spectroscopy. This kind of brings me to the end of this session. I hope you got a basic idea on how SALT works. Saffron works very similarly. It's dedicated to running MIMS ENDOR, so it will also include an effect called blind spots. But we don't have time to look into this in this workshop, unfortunately. So this is the end of this session. We have a short break now. The next session starts in about 17 minutes. Feel free to look through the scripts and try them out, or post some questions or even answer some questions on Slido. And see you then in a little bit.